Okay, so what if I told you that what you're seeing right now isn't a special effect, that it's a real physical phenomenon you could witness with your own eyes? Today, we're diving into the absolutely mind-bending world of quantum levitation. Seriously, there are no wires, no tricks here. Just an object, hanging in space, seemingly ignoring the laws of gravity we all live by. So, how is this possible? What kind of invisible force are we even looking at? All right, what's your first guess? Come on, really think about it. Hidden wires? Some kind of clever camera trick? Or are we looking at something straight out of science fiction? Like anti-gravity? Well, if you guessed any of those, you're in for a surprise. The answer is none of the above. This is real, it's repeatable, and honestly, it's one of the most incredible demonstrations of physics you will ever see. Let's dig in and figure out what's really going on. Now, I bet your mind immediately goes to magnets, right? And hey, that's a great instinct. But as we're about to find out, the simple push and pull of the magnets on your fridge could never create this kind of stable, locked-in-place levitation. In fact, a fundamental law of physics actually says that's impossible. Yeah, it's all thanks to something called Earnshaw's theorem, a principle from way back in 1842. It basically states that you can't create a stable levitating point using only static magnets. It's kind of like trying to balance a marble in midair between two other marbles. You might hit that perfect sweet spot for a split second, but the tiniest little bump, and boom, it's gone. True stability just isn't in the cards. Now, of course, people have found some really clever ways to kind of get around Earnshaw's theorem. Take a toy like the Levitron. It uses the gyroscopic force of a spinning top to create a little pocket of stability. But look closely. It's not locked. It drifts, it wobbles, and that is a huge, crucial difference from what we saw in the beginning. So let's just spell it out, side by side. On the left, you've got your classical levitation, a super delicate balance that's easy to mess up. On the right, you have something way, way more robust. It's not just floating, it is locked. It's a totally rigid, stable connection with zero physical contact. This isn't just floating, this is something else entirely. Okay, so if it's not our everyday magnets, then what in the world is it? Well, the secret lies in a very special class of materials and a truly bizarre property that comes straight out of the quantum world. What you're seeing is called quantum levitation, or to be a little more precise, quantum locking. It's not anti-gravity, it's a special material, a superconductor, being frozen perfectly in place by a magnetic field, creating a stable, three-dimensional lock. And the hero of this entire story is this amazing material called a superconductor. When you cool it down to extremely low temperatures, it basically gets two incredible superpowers. First, its electrical resistance completely disappears. I mean, just imagine a wire where electricity could flow forever without losing even a single drop of energy. Second, and this is the real key to our mystery, it becomes a perfect shield against magnetic fields, actively pushing them away. All right, so let's get into the nuts and bolts here. How does just cooling down a special material create this impossible-looking lock? It's this really cool process that literally brings the weirdness of the quantum world up to a scale that we can see and touch. It all happens in a few key steps. First, we cool the superconductor way down. As it hits that critical temperature, it activates something called the Meissner effect, which tries to push the magnetic field out. But, and this is where the magic happens in step 3, tiny imperfections inside the material act like little anchors, trapping or pinning some of those magnetic field lines. And what you get is this incredible, invisible scaffold that locks the superconductor in place with amazing strength. So let's break that down. First up, the Meissner effect. Think of this as the superconductor's shield. As it cools, it generates these tiny electrical currents on its surface that create an opposing magnetic field, perfectly canceling out the external field trying to get inside. It pretty much becomes a perfect magnetic invisibility cloak. But the real secret, the thing that makes it lock instead of just float, is something called flux pinning. And here's the beautiful paradox. It's the imperfections in the superconductor that make this whole thing possible. While the material is trying to push that magnetic field out, tiny defects act like little hooks, snagging and trapping lines of magnetic flux. Those trapped lines are the source of that incredible locking force. You see, these pinned flux lines create something like a magnetic memory. The superconductor literally remembers its exact position and orientation in space. If you try to move it, those pin lines pull it right back, creating that powerful and stable lock. This memory effect, the technical term is hysteresis, is the real secret sauce behind that rock-solid stability. So you see, it's not just floating, it is locked. Those pinned flux lines act like an invisible rigid structure holding the superconductor exactly where it is. That's why I can glide along a track without ever falling off. It's why I can hang completely upside down and just stay there. Now, this is way more than just a cool science demo. The ability to create a perfectly stable, frictionless lock has the potential to completely revolutionize technology. So let's talk about why this actually matters and some of the mind-blowing possibilities. Just try to picture a world with truly frictionless motion. We're talking about maglev trains that are literally locked to their tracks, capable of incredible speeds with absolute safety, or flywheels that can store energy with almost perfect efficiency, totally transforming our power grids. I mean, this technology could change just about everything, from how we travel right here on Earth to how we explore the stars. Okay, so if this is so amazing, why aren't we all zipping around on quantum-locked maglev trains? Well, the truth is, the challenges are pretty huge. The extreme cold you need, the high cost of the materials, and the sheer difficulty of manufacturing them at a large scale, those are the major hurdles that engineers and scientists are working to overcome right now. All right, let's just take a step back for a second and think about what we've really witnessed here. This is about more than just floating pucks and futuristic trains. It's a rare, profound glimpse into the fundamental nature of our reality. Because this is where it gets really, really cool. Quantum mechanics is usually the world of the impossibly small, that strange, fuzzy dance of atoms and particles. But right here, with quantum levitation, all those bizarre quantum rules suddenly scale up to our world, to an object you can literally hold in your hand. It's this rare, stunning bridge between those two worlds. It proves that there isn't one set of rules for the tiny world and another for ours. It proves that it's all just one reality. Most of the time, those quantum effects just average out and we never notice them. But in a superconductor, they all work together to create something extraordinary. Just one single phenomenon that forces us to completely rethink what's possible. And that leaves us with this incredible, tantalizing question. If quantum mechanics can literally reach out and shape objects we can see and touch, what else might be hiding out there right in plain sight, just waiting for us to find it?